We hear a lot about mental health these days, and we know that mental stress can significantly impact our mental health. In fact, studies have reported that over 80% of university students report feelings of stress or anxiety. Here we can see a student hard at work, clearly stressed about his upcoming biomaterials exam. It'd be great if we could help him somehow, by quantifying his stress. Here we can see another student also studying for his exam, and he has a very interesting method to deal with stress. But there is a better way. To help people better manage their stress, we have developed a wearable device that can quantify stress levels in real time. It works by analyzing the levels of sympathetic and parasympathetic activation. The sympathetic branch of the nervous system is associated with arousal, while the parasympathetic branch helps us relax.
We can measure this with ADA and PPG sensors. ADA stands for electrodermal activity. It measures changes in skin conductivity, which is controlled by the sympathetic nervous system. PPG stands for photoplethysmography. It measures blood pulse using light, allowing us to calculate heart rate variability, which is controlled by the parasympathetic nervous system. Here is a demonstration of our device in real time. Our algorithm calculates stress levels by comparing data from the two sensors that we have here. Our front panels have various indicators for sensor data history, as well as a dial for heart rate. Once stress levels are calculated, they can be displayed here using the onboard LED indicators.
Keeping the PPG and ADA sensors in contact with the user's fingertips was essential for reducing motion artifacts in the signal. Using Fusion 360 for the designs, a PPG sensor holder was 3D printed to be used with a strap. Additionally, wire clips and an ADA sensor slot were made to reduce tangling.
An active filtering circuit was constructed to improve EDA signal quality. The circuit implements a low-pass filter, which eliminates motion artifacts while also amplifying the EDA signal. This improves signal quality and makes the system more robust to noise.
The sensor signals taken from the circuit are then converted to digital signals by the MyRio. This sensor data is then transferred to the PC device and imported into LabVIEW. LabVIEW then sends the data to MATLAB, which applies digital filters to the data and returns various information, in particular the stress value of the user. The stress value is then compared to different threshold levels to determine whether the user is experiencing low stress, medium stress, or high stress. Threshold values were defined through experimental design and comparison of changing heart rates depending on the scenario. The level of stress is then presented on the MyRio LEDs.
Stress classification from our device was calibrated and verified by comparisons with actual stress evoked through physical means. The full potential of our device can be realized through incorporation of transcutaneous electrical nerve stimulation, which, upon activation, can provide immediate and effective stress relaxation during highly stressful conditions.